later. Okay, now strong acids and strong bases are less stable than their weaker acids and weaker bases. So when you have a strong acid and a strong base with each other, what happens is they react and form the weaker conjugates. And by looking at the pKa, and we look for the stronger acid and the stronger base, and then we know that that side is not going to be the side to which the equilibrium shifts. It's going to shift to the weaker conjugate acid, conjugate base side. So basically, let's look at this example down here. Here's an acid, and here is an acid. Let's compare the pKa's. This is a stronger acid. This is a weaker acid. Because this is a weaker acid, that's a stronger base. So whenever you identify, you just look for the acids, and you'll see this is a stronger acid, that's a weaker acid. That means that's a stronger base, and that's a weaker base. It always shifts to the side of the weaker acid and base. So all I ever do is I look at the pKa of the acids, and I say, stronger, weaker, it shifts to the weaker side. Pretty simple idea. So now, using this idea, go ahead and identify to which side does equilibrium lie in each of these reactions. Determine the outcome, and then resume the lecture. Pause and then resume. If we look at this first reaction, you will see the pKa of water is 15.7, nearly 16, and the pKa of acetic acid is 5. This is a stronger acid, so this side of the equilibrium is favored. If I look at ethanol versus ammonia, this is the stronger acid, this is the weaker acid. As a result, this equilibrium is shifted to this side. So what affects the acidity? The key is the stability of the conjugate base. When we look at the stability of the conjugate base, we look for what element is holding the charge, what inductive effects are there. Remember that an inductive effect is an electronegative atom nearby pulling on the negative charge. And is there resonance? And what is the hybridization of the atom which is holding the charge? Because that affects the energy of the orbital that is holding the charge. If we look at the element holding the charge, the trend in the periodic table is, as you go over to the right and down, the acidity increases. So it's the opposite of electronegativity with regards to the columns, but it's the same as electronegativity with regards to the row. Why is this? Well, more electronegative atoms can hold negative charge better. So the trend is, as you go across the periodic table, the atom bound to a hydrogen is better able to hold the negative charge, and so that hydrogen is more acidic. In the row, the electronegativity isn't nearly as important as the size of the atom. Small atoms concentrate charge, and large atoms allow it to spread out, and the orbitals in which the electrons are held are kind of big and easily polarizable, and so it's a more stable state. So what happens is the larger atoms, as you go down, hold charge better, and so if you have, let's say, a sulfur versus oxygen, oxygen's higher, sulfur's lower, a sulfur hydrogen bond is more acidic than an oxygen hydrogen bond. Inductive effects are that you have electronegative atoms nearby that pull on the negative charge. When they pull on that negative charge, they're pulling it back into the molecule where it can be kind of spread out. That is a more stable effect. So the closer electronegative atoms are to an atom that holds negative charge, the more it will stabilize that atom when it takes on negative charge. So if I look at this molecule right here, when it loses a proton, it has a negative charge and there's no electronegative atoms here. But when this loses a proton, the negative charge is pulled over this way slightly by these fluorines. That makes this molecule more acidic. Resonance is very important in determining which is more acidic or in affecting acidity. So if I look at these two molecules down here, they're very similar. The difference is that this has a pi bond next to this oxygen that is going to take the charge, the negative charge, when it loses a proton. So when ethanol loses a proton, what happens? You have the negative charge resides on a single oxygen and it's concentrated on one atom. With acetic acid, when it loses a proton, this negative charge can be in resonance with this oxygen over here and the pi bond there. So what happens is you have not only this structure, but you have this structure. This means the real structure of the acetate ion here is halfway between this and this. So half the negative charge is on this atom, half the negative charge is on this atom. That spreads out the charge and makes it so the anion is more stable. A more stable anion means the proton comes off more easily. Hybridization is important in that the different hybrid orbitals have different energies. Because this is half S, it has lowest energy. Because this is only 1/3 S, it's next lowest. And because this has only 1/4 S character, this has the highest energy. Why? Because P has higher energy than S, so the more S character means the orbital goes down lower. So when we look at these these molecules down here, they have different hybridization, sp3, sp2, and sp. When this atom loses a proton here, the negative charge is going to be in an sp3 orbital. When this atom loses a proton, the negative charge is held in an sp2 orbital. And when this atom loses a proton, the negative charge is held in an sp orbital. That means that this is the weakest acid because that negative charge is going to be in a high energy orbital. This is the strongest acid because that negative charge is held in a low energy orbital. And we actually find that we can deprotonate this right here, this acetylene anion, with something like sodium amide. With this ethane, it's very difficult to deprotonate, and to deprotonate it, you have to go through some to actually get the anion, you would have to go through multiple steps and first react it and get it to have a halogen here, and then react a halogen with a metal, and it's just a much longer route. Why? Because this is so much less acidic and you don't have a strong enough base to go and deprotonate it. So now, using what you've learned, determine which will be the stronger acid in each pair and explain why. What is the principle that you're using to determine this? Pause the lecture and resume after you finish this. Okay, now the weaker acid here is going to be water. The stronger acid is going to be hydrogen sulfide. Why? Because sulfur is a bigger atom and it can hold the negative charge better. And remember, the trend in acidity is as you go to the right and down, atoms become, the hydrogens attached to those atoms become more acidic. In this pair, you have a carbon and you have a nitrogen. Nitrogen is much more electronegative than carbon. And so what we find is this is more acidic than this molecule. Ammonia is more acidic. And remember, you're using the trend as you go to the right and down in the periodic table, you have a more acidic atom. Okay, let's look at this. Here we have sp2 hybridization on the carbon, here sp. This is going to be more stable because sp hybridization gives a lower energy non-bonding pair. And then down here, when we look at these two molecules, the difference is the fluorines. Fluorines are an electronegative atom, and so they inductively stabilize that negative charge. And so the trifluoromethanol is a significantly stronger acid than just plain methanol. Which is going to be the stronger base in each pair? Remember, what you have to do to determine a stronger base is look at the acid. If a molecule is a stronger acid, then its base is going to be its conjugate base will be the weaker base. So keep in mind, that's how you determine these. Determine which one will be the stronger base, and then resume the lecture. If we look at these two, we would find that hydroxide will be the stronger base. The hydrogen sulfide was the stronger acid. So that means water, the weaker acid, produces the stronger conjugate base. If I look at these two, ammonia was the stronger acid. So that means that the methyl anion is going to be the stronger base. If I look at these two, the conjugate acid of this base right here was the weaker acid. So this is the stronger base. The conjugate acid of this was acetylene. It was the stronger acid, so this is a weaker base. If I look at trifluoromethanol, it was the stronger acid, so this is a weaker base. Methanol was the weaker acid, so this is a stronger base. Okay, organic bases have lone pairs that allow them to reach out and grab protons. They actually use their non-bonding pair to reach out and form a bond with that proton through overlap with the empty orbital on the hydrogen. The more negative charge you have on something, the more basic it's going to be, and the more it's going to want to grab that proton. So if I look at these atoms, they're all neutral. So all you have to do is look at the atoms and compare their characteristics, and that will tell you about their basicity. Which is more basic here? This one with a proton on the oxygen, or this one with a negative charge on the oxygen? Of course, you should say the negative charge makes the anion more basic, so the acetate here is more basic. Okay, the Lewis acids and Lewis base definition is that a Lewis base has a non-bonding pair to give up to a Lewis acid, which has an empty orbital. And this really is just a reaction occurring where you have orbital that's empty with an orbital that's completely full, and when they overlap, they form a bond. So it's natural that this would happen, but we still call this a Lewis base and this a Lewis acid because it fits the definition of those two things. There's no scale of strength to use here. This is the Lewis acid and base reaction is just a tool to explain that you have a non-bonding pair that's overlapping with an empty orbital to form a bond. We use curve arrows for this. So in acid-base reactions, we're always going to be using a curved arrow to show a non-bonding pair reaching out to find an empty orbital. When a non-bonding pair reaches out and finds an empty orbital, it forms a bond here. So you see how this is reaching out and grabbing that boron that has an empty bond? That becomes a bond. Now, because electrons are going to boron, boron has to get a negative charge. Because electrons are leaving the oxygen has to get a positive charge. Go ahead and draw the arrow showing the Lewis acid-base reaction that's occurring here. Remember, what does an arrow show? An arrow does not show movement of the atom. An arrow is showing the movement of the electrons to form or break bonds. So draw in your arrow and then resume the lecture to get your answer. Because the non-bonding pair has to reach out and grab the empty orbital here and form the bond with it, we draw the arrow going from the negative charge to the positive charge, and then afterwards, because negative left the oxygen to form a bond, it doesn't have a charge. And because positive gained negative to form the bond, it doesn't have a charge, and this is neutral overall.